There we go. That's me. I am a freelance developer advocate, and one of my previous jobs was at a cloud company, a cloud provider, not one of the big ones, but we dealt quite a bit with a lot of data, code, media, whatever. And I started learning about how and why we store data in the way that we do as an industry, how we did it at my particular employer at the time. And I went down a lot of rabbit holes, and I came out with this talk. So today we are going to be talking about data storage. Before we get properly started, it's worth asking, what is this concept that I'm going to be talking about today? One of the ways I like to describe it is in the Sherlock Holmes stories, the titular detective says that he doesn't know that the Earth revolves around the sun. And he defends this lack of knowledge by saying that like every piece of knowledge he has is like a piece of luggage taking up space in an attic. His brain is like an attic crammed full of knowledge. And if he wanted to keep knowledge about the sun going around, the Earth going around the sun, he would have to kick out something that was more useful. Obviously, like our brains don't work quite like that necessarily, but the general principle stands. We need to know more things in our day-to-day life, especially as the world gets more and more complicated, than we can fit in our heads. So, for example, how many people in this room would say they know 3 phone numbers by heart? 4? 5? Right? We need to know more things than we can remember. And that means we need to store them somewhere. But you can't store ideas, you can only store objects. So in order to store information, we have to turn it into a physical object. This talk is about how we as a species have done that historically, how computers have impacted the ways that we do that and the problems that we run into doing that. In terms of computers, I'm going to talk specifically about non-volatile memory. So memory that doesn't lose its state when it loses its power. So we're not talking about, for example, RAM. One thing I'm also going to touch on is the durability of data storage, which has 2 aspects to it, 2 kind of flavors. Obviously, when you turn ideas into objects, the physical durability of that object matters. If you can tear up a piece of paper or, snap a CD in half, that's part of what makes data durable or not durable. But the other half is about the encodings that we use, the way that information is transformed when we turn it into a physical object. If we lose the ability to transform it back and forth, we also lose the data. So who can tell me, without getting out their phones, where this leads? So that's not very durable, right? If you don't have your phone, you can't interpret this data. So that's one of the things that we need to be careful of when we talk about storing data, is not just what's the object that we're turning it into, but how we do that transformation. So what I'm going to talk about today is I'm going to go through old ways of storing data. So this is no electricity. Before we sort of harnessed electricity, how did we store data? We've got old things which did use electricity, so a lot of the fun history of computing. We've got things that we use and know and love and maybe hate today. And then for a bit of fun, I'm going to talk about things that we might use in the future. I make no promises as to the accuracy of any of the things that I talk about in this section, but they are very cool. So let's get started. Old stuff. First up, we've got clay tablets. These were traditionally not fired in a kiln, but instead they were left to air dry. And as a result, we don't have a lot of these. The one that was up here was actually found in the ruins of a guy's house that had burned down, and the fire that burned his house down fired the clay tablet, and that's why we still have it. And this guy had a really, really bad time, right, because his house burned down, and as a result, we now know what's on this clay tablet, which is a complaint about how shitty of a copper merchant he was. Has anyone heard of Ian Nazir before? Yeah. This is the Ian Nazir tablet. It is probably, it's the oldest known written customer complaint. It's about this guy's house that burned down. And it's one of a few that were found in his house. So the writing on this tablet is Akkadian cuneiform. For a long time, we could not read this. Linguists in the 18th and 19th century all got together. They went, well, this is clearly language. We'd like to be able to read it. And they got together and they sort of reverse engineered the Akkadian cuneiform that's on this tablet. So now we can decode it, but for a long time, that encipherment was lost. So while the object here is very durable physically, although that's only by chance, the encoding of the data on it wasn't durable. We lost it for a long, long time. Clay tablets. When I said history of data storage, I meant like we're going back to the Bronze Age. Another thing that I'm going to talk about is on the other end of the physical durability spectrum. We've got pen and paper, ink and parchment, pigments on papyrus, so on. Again, the encoding here, like with the clay tablet, is written language. So to be able to get data out of this thing, we have to know the language. The photo of this photo is the first 2 pages of the Beowulf manuscript. And we don't actually know when this was written, sometime between 975 and 1025 CE, so about 3,000 years ago. No, sorry, 1,000 years ago, sorry. We don't know when the poem itself was originally composed. This is the only copy of it that we have. Now, this is a foundational text in the study of Old English, and we only have the one copy of it. This manuscript formed part of a library called the Cotton Library, after a guy called Cotton who had a fondness for old and weird stuff, like me. And for a time, this Cotton Library was stored in a building called Ashburnham House. Does anyone want to guess what happened to Ashburnham House? Like Ian Nazir's house, it caught fire. And unlike with clay tablets, fire is very bad for the durability of paper and parchment and manuscripts. And so the Beowulf manuscript, it survived the fire, but it did suffer some damage, and it's continued to accrue damage since then as a result. So again, you've got this not very durable physical medium, but we can read Old English and we can get the data back out of it. And this is all very interesting, and you might be thinking, this is very cool, but this is supposed to be a tech talk. What did any of this have to do with technology? Well, now I get to share one of my favorite facts with you. The English word technology comes from the same root, European and Proto-Indo-European root, as the word for textiles. Historically, this makes a lot of sense because as humans, things that we've needed to do in the past are like find enough shelter so we don't die of exposure, grow enough food to eat, and produce enough cloth to make things like clothing and sails for ships and bedding. So for a long time, textiles were like the site of technological advancement in human societies. For example, if you spend time looking at medieval manuscripts, as I am known to do, you will often see women with drop spindles. That's what this woman is holding here, this big long stick with the sort of pointy bit at the top. I have a laser. Yeah, but the pointy bit at the top is called a distaff. And then here she's got a drop spindle, and you can see her cat is bothering her, which if you do yarn crafts, you will know is absolutely true to life. And the thing about this illustration is that you see so many of these because as a woman in the 12th century, if you had 5 spare minutes, no, you didn't. You needed to spend it spinning fiber from your sheep into yarn to be used in textiles, because that was like the single most important thing you could be spending your time doing. We get the English idiom to spin a yarn, meaning to tell a story or to tell a tale, because women would sit together with their drop spindles and their distaffs and tell each other stories while spinning yarn. So, how do we actually turn that yarn into cloth? Well, this is a loom in 2nd century China. They invented the draw loom, which is a machine for weaving thread into fabric, which obviously massively sped up this process of making fabric, which we definitely need. And you can see here that the fabric is it's not that fancy, right? It's got some stripes. And we needed fabric. We do still need fabric. And we'll make do with fabric that's plain or not that fancy. But what we really like is really fancy fabric. But to make that, each of these individual threads, both the ones that go up and down and the ones that are woven back and forth, you need to select them very carefully according to their color on each pass of, passing some threads through and some threads over, right? This is labor intensive and time consuming and very difficult to do without error. If only there was some way we could sort of get that pattern information that we know what it's going to be based on the colors of the strings and get some way to encode that so that the loom could do it automatically. And this is where we get punch cards. So how this works is as follows, for each little thread, what it is when you use a loom is you have some threads that go up, you've got threads that go this way and you separate them out, right? And then you've got some other threads that go back and forth. So this is the warp, these are the warp threads, and these are the weft threads. And for each thread in the warp, you want to decide which ones go up and which ones go down based on what color they are. And so for each pass, what you can do is you can have a little hook that comes down and goes, do I want to pull this thread up or do I not want to pull this thread up? And the hook can pass through the punch card if there is a hole there and pick up the thread. And it cannot pass through if there is no hole there. So depending on whether or not there's a hole in your punch card, you will or will not select a thread to go into the bit of the warp that goes up or not. Ones and zeros. And so what you have here is you have pattern data encoded into binary. And this is called a jacquard head. A loom with a jacquard head on it is called a jacquard loom. And they let you get fancy fabric with much, much better precision, much, much lower labor costs, fewer children getting caught in the machinery of all the looms and getting like crushed to death, which was genuinely a problem. And also it gave rise to computers, but like fancy fabric. Here is some fancy fabric that was made with a jacquard loom. And the ideas behind this technology were developed by a few different artisans in the 1700s in France, ending with the guy called Joseph Marie Jacquard, where it gets its name. And the patterns from punch cards that were made in the 1700s are still in use today. So a big win for data durability. We know what that data meant, and we have the objects that we use to encode it, and we can still use them. That's super cool. Right, photography, film photography. Is anyone here like a film photography buff, like really into film photographs? Okay, cool. This will be new to all of you then, probably. This is the earliest image derived from a photographic process. Whether or not you can call it a photograph is sort of a bit up in the air. What's on the left is the earliest photographic plate, and on the right is a colorized version of the resulting image. And this is a building, like that's the horizon there, and this is the view out of a guy's window that he captured. It was created by a guy called Nicéphore Niepce, I'm probably mispronouncing that, in 1826. And what he did was he used a camera obscura, which is you take a little pinhole in a sort of a surface, and light filters through that pinhole and ends up projecting an image of whatever's on the other side onto a surface, and it will be upside down. And the thing that he projected that light onto was a photosensitive substance called bitumen of Judea, and it hardened differently depending on what kind of light hit it. So what you end up doing is encoding that light information that's hitting the plate into texture, and then you can use that texture to make prints that represent the visuals of the light that hit that plate. Yeah, I think that's really, really cool. It's really interesting also as far as data storage goes, because the encoding itself has very little human input. It's a chemical process. There's no language involved here. There's not a lot of, all of the subjectivity of photography is in what you choose to capture, rather, or this kind of photography, what you choose to capture and not how the actual chemical processes occur. Which I think that's unusual among all of the kinds of data storage that I'm talking about today, pretty much, apart from also vinyl discs, which I'm talking about next. But yeah, film photography. Cool little factoid. This is a daguerreotype, one of the slightly later forms of film photography, first publicly available kind of film photography. It kind of democratized the entire thing. And this is very possibly the first candid photo ever. You can see just there, you can see a guy getting his shoe shined and the person doing it. The exposure time for this kind of photograph or daguerreotype was about 4 or 5 minutes. And most people on this street weren't staying still for that long, right? They were walking up and down and they don't really show up in the resulting image. But this guy and the guy shining his shoe do. And they probably never knew that they were the first people ever to be the subjects of a candid photograph, which is really, really cool. Obviously, film photography has continued to progress as a discipline. Daguerreotypes like this one here was superseded by collodion photographs, which are still used by hobbyists and amateur, well, professional film photographers today. And more photosensitive substances have allowed us to keep developing this discipline. Right. Vinyl audio records. Here we see the first example of a paradigm that's going to come up again and again throughout this talk, which is you have a disc and it spins round and round, and then you have a head, you have like a needle here that reads data off that disc as it spins, and you encode, like, data is sort of stored on the disc in concentric circles or in a very gradually increasing spiral. So here, what the data is it's audio, and it's encoded as texture. The arm goes up and up and down, and in most modern players, what that does is it translates to an electrical signal that we then render into audio. So the head here, just a little needle. Is anyone here, I should probably ask this about a lot of the things I talk about, is anyone here a vinyl collector? Okay, a handful. Yeah, You have a little needle, and record tape players take the signal that it produces and turns it into audio. So when we come to things about thinking about data durability for this kind of storage, the data here is encoded in the texture of the disk. And the disk itself doesn't have any kind of protective layer over it. It can't because of the way that the needle needs to read from it. So you have to be super careful when handling them. We actually get the phrase like a broken record from what happens if you get a scratch on the surface and the needle just like skips back and then plays the previous bit again. That's why like a broken record means repetitive, because that's what happens if you get a scratch on the surface of one of these, or what can happen. Physically, they're pretty fragile and they need pretty specialized equipment to play. So in terms of data durability, they're pretty fragile, but also they offer an incredible sort of high quality, which is why they have persisted as this sort of people collect them and listen to them, even though they require very specialist equipment and they're quite difficult to take care of physically. Right, we are now into the wonderful world of computers, electricity, magnetism. And we're going to go back to punch cards. So punch cards round two, a guy called Herman Hollerith, he developed machines for tabulating census data for the US 1890 census. All that data was stored on punch cards, and he later founded a company that got merged with a few other companies and eventually became the entity that we know and love today as IBM. So IBM essentially popularized punch cards. The concept here is the same as with the loom. A hole in the card allows some kind of connection to be made that triggers a process. In Hollerith's tabulating machines, the connection that's made is a spring that drops down and dips into a pool of liquid mercury, allowing an electrical connection to be made, which is obviously very safe and normal and healthy to be around for long periods of time. Something you might notice about this is that there are 80 characters on this punch card, sort of runs from 1 to 80, just to do with like the physical size of these things. It was how they were manufactured. We see the legacy of this today in systems that assume that you want 80 characters in your terminal, or maybe 79, depending on what kind of delimiter you're using. 80 characters per line comes from punch cards. Punch cards were eventually superseded They were eventually superseded by magnetic storage of various kinds in terms of long-term data storage. There's a photo that I meant to put in these slides of somebody with a stack of data of punch cards, and it's like their PhD thesis or something. They're a computing student at some point in, I think, the 70s. And what they've done is they've got this stack of cards, and they've drawn a line that goes diagonally across them, like, sort of across the ends of each of these. And it's so that if they get out of order, they know how to put them back into order. Because if you've got these punch cards, if you drop them and they shuffled everywhere, it's like somebody scrambled your code, right? You need to be able to put them back into order, and that was how they chose to do it, which I thought was really cool. So, punch cards. And then these are not intrinsically electrical, but they were used in the electrical early computing context. We now come on to drum memory. We've got more spinning things. And now, the spinning things, we are cooking with magnets. Magnetic storage works like this. You have some kind of ferromagnetic material, that's iron, cobalt, nickel, certain rare earth metals, and you arrange that metals, those ferromagnetic materials, in some kind of a crystalline structure. And then you can polarize that material by using magnets to polarize certain areas one way or another to represent essentially binary data, which way round is this area polarized. Drum memory works by having a drum, that's just a cylinder, coated in that magnetic material, and heads, or just a single head, that can read or write that material. So it can either detect the polarity or change the polarity of the material at that point. Data is stored in tracks, which are like circles around the surface of the drum, and various different types of drum memory at various points have done. So here you can see, actually I don't know how many heads this has, but this is the first one. This, I think, is, the best. This is like one of the first bits of drum memory ever made. But this one is called the ZAM41. This is a Polish one. And the thing that's interesting about this one is it has one read-write head for every track. Because when you're dealing with your spinning disks and heads that read and write to them, sometimes if your surface is very large and you've just got one head, it'll take a long time to physically move the head into the position that it needs to be in order to read data. And this time is called the seek time. And you want generally to minimize that because especially if you're using these for like the working memory of your computer, that matters like a lot. But if you want, the one way to minimize it is to have multiple read-write heads, which is what this does. It has one per track. So for every layer that you're sort of storing data on your drum, there's a read-write head specifically dedicated to that one track. But it's really expensive to do. And not many of these got made, and they did not become popular, even though they drastically reduced computing time, because it was just really expensive to build and maintain these. We now come on to magnetic core memory. This was the dominant form of random access memory storage for decades, and it was so ubiquitous that it was often just referred to as core memory or core. And the way that this works is it's also magnets. These ones don't spin, though. Each of these rings is made of magnetic material, and what you've got running through them is copper wire, so generally at least 3 bits of copper wire per ring. And by running currents through those copper wires, you can change the magnetism of each of those rings. So each of those rings represents a little bit. Reading from a core also requires running a current through or generating a current. And what that does is it wipes the magnetism from that ring. What that means is that when you read data from memories that's stored this way, you also destroy that data. It's destructive readout. So you can't copy data in this way. What you have to do is you have to read it out and then maybe store it in 2 places. Oh yeah, one neat thing about this kind of memory is that it was heated rather than cooled in order to make it more efficient. The thing that makes this kind of memory efficient is having a consistent temperature, and it's a lot easier to manage that by heating something up than by cooling it down. So if you're having problems with your PC at home and it's getting too hot, and you maybe install some core memory and it will just take advantage of all of that heat. Using smaller and smaller cores and wires basically lets you much more densely store information in the same physical space. But manufacturing that as you get smaller and smaller becomes very cost intensive, very labor intensive. And this is a process that had to be done by hand. So for working memory of your computer, this was eventually superseded by RAM, which is a volatile memory, and I won't be covering it, but it's also very cool. We get the phrase core dump from this kind of memory because this kind of memory does not lose its data when it loses power. This is not volatile memory. And so if your computer had an issue, you could dump the working memory, the working state of the computer at the time that it had that issue would still be in here. It would be dumped in this core. That's where you get a core dump from. This is one of my favorite things in the whole talk. This is memory. This is memory, but this is actually a program. This is actually a computer program. This is software, and it's core rote memory, and it's read-only memory. And what happens here is the process of writing to this memory is done during its construction. How you thread that copper wire through these rings encodes information. Which way round, sort of ones and zeros, you can kind of see how that would map. To update this software, you've got to do all kinds of complicated threading and unthreading and rewiring. And this type of memory got the name LOL memory or LOL memory for little old ladies, because the process of manufacturing this and writing to it looked like sort of some kind of threadcraft, like knitting or crochet or whatever. You look like little old ladies doing it. The most famous usage of this was in the Apollo missions, and it was used for that because it's really hard for this to change. Like you can't. With core memory, for example, you can imagine that there might be, and something else I'll come on to later when we talk about hard disks, is sort of random effects that could maybe flip a bit, right? And then suddenly you have an error. That's really hard for that to happen here because it's about how the wire is threaded through rings. This is really, really stable and durable physically once it's been constructed. So if you want something that you know you don't want to do updates to, like your software for your spacecraft once it's already in flight, and you want to make sure that it stays stable, this is great for that. So that's really cool. I like that. I just like, it's a piece of software and it's just there, it's physical. Right. Now we come on to something that I feel very sad about putting in the old section. That is floppy disks in the historical section. Seen here in 8-inch, 5¼ inch and 3½ inch sizes. These were the latest and greatest in removable storage media from about the mid-1970s to the early 2000s. And has anyone ever opened up a floppy disk before? Yeah, that's why they're called floppy disks. You open them up, and in the inside is magnetic sort of tape, film sort of material. And again, it's a spinning disk. It's a spinning disk with stuff recorded on it and tracks. And when you put it in your computer, the disk spins and something reads off it. This is what like a naked floppy disk looks like. This is the innards of a 3.5-inch floppy disk. And if you picked it up and shook it, it goes whoop, 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 and it's very satisfying. But it doesn't work again after that very well. Here's what it looks like really close up, and you can actually see the way that it curves. It sort of curves like this, obviously much less extreme than I'm doing with the laser pointer. But yeah, you can see the tracks. This was a photograph taken with what's called a magnetic field camera, and it detects magnetization. So the bright and dark areas are areas of magnetic polarization on the surface of this floppy disk. Yeah. Of course, this means that if you put a magnet near it, you will destroy the data that is encoded using magnetism. So don't do that. Again, one of my favorite images on the internet. One thing that's interesting about floppy disks and the spinning disk kind of method in general is when you think about the way that data is encoded on disks, it's a bit like this. Here we can see sort of two tracks, right? And I've sort of highlighted them in one sector. So memory would be addressed like per track or per sector and then per track, or vice versa, it doesn't really matter. But you've got sort of, the thing that I want to point out is that each of these lines would take the same time to read from as the disk spins at a constant rate. You know, the head that hovers over here or over here is going to be reading for the same amount of time as it traverses here or if it was traversing here. And what that means is that when you store data, if you want your head to be reading every however many microseconds or whatever, you get to store much data much more densely towards the center than you do on the edge, because here the disk is moving faster because the track is longer, so your data has to be much more spread out, and this is inefficient. You're not using the surface of the magnetism here as efficiently as you are towards the center. And if you care very much about like optimizing the use of your magnetic material, you don't want to do this. You like to store data much more densely at the outside. But what that means is that when you're reading from the outer edge of the disk, your disk has to be spinning more slowly. You can't have constant angular velocity. You'd have to have variable angular velocity. Apple tried to do this. They tried to build floppy disks that worked that way so that they could optimize the amount of storage that they put on each bit of the spinning disk. But what this meant is that disks encoded, written to in this way, could not be read from in a floppy disk drive that was not using the same technology. One that tried to read from a disk written with this variable angular velocity technology. If you tried to put it in a standard constant angular velocity disk drive, you'd get garbage out because that's not how it was written. The encoding of the data was not durable in that way. It required very specialized technology, even more specialized than the floppy disk drive already is. So it was expensive to manufacture and to maintain, and they never caught on. And so this is the model that most spinning disk technology uses, is it's just less efficient at the outer edge. But it means that we have much more simple technology and hardware in order to read and write these things. Because the encoding of the data being easy to, read and write to matters more than the physical efficiency of the medium. So before computing environments were regularly networked, floppy disks were the go-to way to share data between different computers. And of course, this legacy lives on, with the floppy disks being the global symbol for the save button. While I was writing this talk back in last year, before NDC Oslo, I think about 13 people came up to me, looked at this slide and went, "You're talking about the save icon." And these are 50-year-old speakers who are doing it as a bit, but it really is a sort of thing. It's that's the save icon. And that's the legacy that it has, essentially, because they are now, Wikipedia calls them obsolescent. In February 2003, Dell announced that they would no longer pre-install floppy disk drives on their flagship home computer. And by 2007, only 2% of home computers or computers sold in stores had built-in drives. I grew up using floppy disks for up until I was about a teenager, and then USB thumb drives became the thing. So I'm that's how old I am. So it's, they are still around. You can still buy adapters for them. The US nuclear weapons don't use floppy disks anymore, but this article came out in 2019. So it's not that far into the past that these were still being used in really, really critical systems, simply because they work, and if it ain't broke, don't fix it. And another thing about floppy disks is that the magnetism on them is very, very stable over time. Like a floppy disk that you had written to 20 years ago, if you can find a way to plug it into something today, very likely to still be readable. And you can still do that today. I went on Amazon, I looked for external floppy disk drives. You can get them. I didn't find any that were USB-C connected, but I did find lots that were USB-A. So, they haven't kept up with the late, like you don't have ones that you can plug into your MacBook that only has USB-C. You'll need an adapter, but you can still read data from a 3.5-inch floppy disk if you have one. Yeah, obsolescent, which I think is just an incredible word. Oh, and I have floppy disk stickers actually after this. Don't let me forget to give you all stickers. Right, current stuff that we know and love and use today. First up, we've got more spinning disks, optical disks. Who here has a desktop PC or a laptop with a CD drive in it? Okay, a handful. Who has a gaming console with a disk drive in it? Yeah, more, right? This is why they're in the modern section. It's like they're not that widely used in day-to-day life, except for, your PS5 might still have a disk drive. So under this category, I'm grouping a bunch of things together. Optical discs include like CDs, Laserdisc, writable CDs, Blu-rays, DVDs. They all work in pretty much the same way. They all use the same paradigm as vinyl and floppy disks and drum memory. You've got a thing that spins and a head that reads from it, or something reading data off it as it spins. And optical media looks like this. You've got bumps and dips in some polycarbonate plastic, and that encodes ones and zeros, essentially. Then you've got a reflective layer of usually aluminium, but not always, depending on the type of disc. And then you've got some acrylic to keep it flat and keep it safe, and you might have a label on the top. And the way that these work is that a laser shines down onto this surface, and how reflective that surface is depends on where it is in this kind of structure and texture of the bumps, and the laser will be able to tell whether it's looking at a bump or a dip. This is a detector. This is a lens from an Acer laptop CD disk drive, I think, or some kind of optical disk drive. And this is a laser diode paired with a laser detector, and it's detecting the reflectivity of the disk surface at each point. So CD-ROMs, ROM standing for read-only memory, they were developed by Sony in 1984, and it wasn't until 1997 that we got rewritable CDs. Now, this is a rewritable CD, and you can notice that it's actually got a much darker reflective surface than the read-only one that was the first image in this section. And that is because it's not aluminium that's providing their reflectivity there. It's actually, it's an alloy. It is a silver indium antimony tellurium alloy. Try saying that 3 times fast after the party tomorrow night. And what this does is it allows that laser diode in the laptop disk drive to actually melt that metal coating. And what happens when it does that is that the metal coating goes from being this kind of crystalline structure to being like this kind of goopy just mess. And then it's solid, but it's lost a crystalline structure. That changes the reflectivity, which is what the laser diode reads. And so it interprets it in the same way that the bumps and dips in a CD-ROM are interpreted. So you can actually write with the laser diode to this disk as well as read from it. However, in order to undo that process of turning the crystalline structure into goop, you have to heat the disk up. Really, you have to heat it up quite hot. And you can't do that to like one specific point at once, really. You have to heat the whole disk up. So if you want to erase what you've written onto a rewritable CD, you have to do it all at once. And that's what burning a CD is. Reading data out of an optical disk requires it to be optically legible. Like it has to look good. It has to be legible to that laser, which means that if you've got grease and dust and whatever on the surface of these, I mean, has anybody here not had the experience of playing music on a CD and it's got a fingerprint on it and it goes all weird? Yeah, like you know exactly what I'm talking about. Unlike floppy disks, these don't have protective cases to protect them from that kind of thing. You can also break them quite dramatically. This is a video of the slow-mo guys who were some, I don't know if they're still going, but they did high-speed camera capture of just like weird things like shooting a bullet into jelly or doing oil painting or whatever. They span a CD so fast that it just shattered. And something to note about this kind of data storage, and it's true of the spinning disks in general, is that once something like this has happened to it, you cannot recover the data because it would require like lining up all the tracks and like reconciling all the damage that's done at those edges. Unlike, for example, shattering a clay tablet, where you could piece it back together and maybe be able to read what's been written there. So in terms of the physical durability of these media, it's actually got a sort of a different failure mode than some of the more analog, like pen and paper clay tablets. I also really don't envy them having to clean up all the little tiny shards of CD-ROM that they caused by doing this. But it's a really cool video. I encourage you to check it out. Right. Something else that's still in use today, which you might not realize based off the image that I'm about to show you, is magnetic tapes. So here we have an example of a data storage medium which is not random access read. Unlike hard drives and flash memory, where you can kind of like, well, flash memory haven't covered yet, but unlike hard drives, for example, where if you want to read from a specific purpose, part of the surface, you can move your head over and there's a fairly short maximum seek time for that, right? It's not going to take too long. It's got good random access. But magnetic tapes don't, because if you're 25% the way through listening to Rick Astley and you want to go to 75% the way through, you have to scroll through that 50%. It's linear seek time in how far away your data is, how far away you are from where you want to be. And this is true of any kind of data stored on magnetic tapes, basically. So we all know how this goes by now. The tapes are made of a ferromagnetic material. It's polarized, ones and zeros. And the hardware that reads and writes to the tape is known as a tape drive. The first magnetic tapes were used to record computer data in 1951 for the UNIVAC 1, also an IBM thing. Oh, sorry, no, that wasn't an IBM thing, but IBM quickly followed suit and set the standards for the industry when use of magnetic tapes ever since. And they have been in constant use since then, pretty much. And despite the drawback of that slow random access time, or potentially very slow random access time, they are very durable magnetism-wise. I mentioned this with floppy disks. It's the same thing. You can shove these in a cupboard for a few years and nothing bad will happen to the data that's stored on them. They're very easily removable from their surroundings. You don't have to keep them powered on. You don't have to keep them anywhere near the things that are used to read from them, which means that also the data that's stored on them is not vulnerable to computational attack. However, if you've got data in a data center that's stored on a tape that is just sitting in a room and has been removed from the computer, it's going to take a while if you want that data, because somebody has to physically go and get it and put it in a machine and scroll to the right bit of the tape. So it's got quite a high latency of access to these datas when data is stored on these in, for example, cloud companies store this. And this is one of the things that I learned when I was working at the cloud company that I worked for last year, is that these are very often used for glacier storage. If you've got sort of blob storage that you've got somewhere that you never look at and it's in cold storage, there's a very good chance it's stored on magnetic tapes. And slow access times then are an acceptable constraint, because if you're using it to store legal data that you need to keep for compliance reasons and you don't need regularly, it's fine that it might take 24 hours for that to become available to you. Last note on magnetic tapes, one of the most famous examples of something called the digital dark age, which is the idea that if we lose access to our encodings, we lose all that data regardless if we still have the physical objects. So the failure mode of that second kind of data durability that I talked about. One of the most famous examples of this happening is the NASA mission, the Viking lander on Mars. Here you can see Carl Sagan next to a model. They did not actually send him to Mars also, unfortunately. That would have been really cool. And this rover this lander recorded a bunch of data to magnetic tapes. NASA got the tapes back in 1976 or 7, I'm not quite sure. They got the tapes back and then they put them in a cupboard for 10 years. And when they got around to trying to read them, they couldn't, because all the engineers who'd worked on this project originally had either left NASA or had died. And nobody knew what the ones and zeros on the tapes meant. And they actually had to go and look at like the physical hardware of the Viking lander in order to try and reverse engineer what it was doing in order to put the data onto those tapes. They lost the encoding. If they had looked at those tapes a little bit earlier, Or if the people who had designed the encodings had written them down somewhere that the people in 10 years' time were able to find, they would have been able to avoid that. So yeah, the loss of the encoding very nearly lost the data that was gained from sending a rover to Mars or sending a lander to Mars. That's a lot of effort to waste. Right, more spinning disks. Can you believe how many spinning disks we have? Hard drives, we all use them, know them, love them. You get them built into most personal computers these days, unless you're an SSD-only person. And you can get an external ones that you can fill with lots of pirated media. And I checked the other day, and it looks like about 20 terabytes is commercially available now. They're expensive, but that's a lot of movies, right? Wikipedia says that 26 terabytes are available as of last year, but I couldn't find any on Amazon or Seagate or whoever. So these, again, the same paradigm as floppy disks and optical media. This metal disk in the middle spins around. You have a head that reads and writes to it. And this is, again, stored ferromagnetically. This is a magnetized material. But they've got cases around them, so you're unlikely to put a magnet near enough to them that you're going to damage the data that's stored on them. Once again, IBM, who pioneered these, and the first one came out in 1957 and stored a whopping 3.75 of God's own megabytes of data. Here you can see two of them. And these are each 3.75 megabytes. These had 52 disks each holding 2 read-write heads, and IBM kept iterating and improving, and we got to where we are today. They also did, so again with the, on the theme of things being technically better but too expensive to maintain and produce, IBM did toy with a model called the IBM 2305, and that had 1 read-write head per track of data, again with tracks being like those concentric circles, and meant that you didn't have any seek time, basically minimal seek time, as good as you can get. Again, too expensive to maintain, they stopped making them. Over the 1980s, hard drives went from being very expensive as an add-on to your home PC to being just the standard, essentially. Here we can see, again, magnetic field camera taking an image of the disk surface. Here's one of my favorite facts that I've ever learned. We have got to the stage where the areas that we are magnetizing on this surface, they've got so small that they start to get affected by a quantum effect called superparamagnetism. And what that does, what happens when superparamagnetism happens, is that heat can cause magnetized material to flip its polarity, right? The thing that I was saying would never happen with the core memory, it can happen with these. It's known to happen in magnetized areas smaller than 50 nanometers. So for reference, the thickness of a piece of copy paper, like printer paper, is anywhere between 70,000 to 180,000 nanometers. We're talking about areas that are less than 50 here, really tiny. We made the magnet so small that the universe doesn't like it. It's so cool. And the way that we counter this is you actually have 2 of these disks next to each other, separated by a 3-atom thick layer of ruthenium, which is not ferromagnetic, it's not magnetically active. And the 2 disks, sitting very, very close to each other, are polarized oppositely, and then they attract to each other and reinforce each other's magnetism. And this counteracts the effect of the superparamagnetism, which is just really, really cool. And that's hard drives. So going back to, these are some photos of a data storage bunker underneath Paris. This belongs to my previous employer, a cloud company called Scaleway. And this is their cold storage, and it's not magnetic tape storage. They actually use hard drives for this, which is fairly unusual. This data bunker is 25 meters underneath Paris. I don't know how close it is to the catacombs. And these are the only photos I could find. They keep this stuff locked down. And the storage mechanism that they use here is they use these hard drives in slightly different ways than we use the ones that are on, say, your laptop or in most data centers that are using hard drives for anything other than cold storage. So when you write data to a hard drive, you have a head that reads and a head that writes, and sometimes they're the same head. And when you write to a hard drive, you write in quite a wide circle, like a fat donut, right? But when you're reading, you don't need the entirety of the width of that fat donut. You could have a fairly skinny donut that you're reading from. Does that make sense? The width that you need in order to read data is much narrower than the width that is written to by the write head. And in everyday hard disk drives, that's fine. It's a little bit inefficient. You're writing to more of the surface than you need to. But it's fine. That's what is called parallel magnetic recording, where the write head and the read head just operate on the same tracks, and they're just very wide. In this cold storage facility, what they do instead is they do something called shingled magnetic recording. So what happens is you start in the center of the disk and you write a fat donut, and then you move a very little bit outwards and you write another fat donut that almost entirely covers the first one and leaves a thin strip, unedited, that can still be read from. And then you do that and you do that and you do that, and it's sort of like you're layering up these strips like the shingles on a house, and it's called shingled magnetic recording. And what this does is it lets you be much, much denser with the information that you store to your hard drive. Much, much better data density. But the trade-off is that if you wanted to go back into the middle of that and write, you'd suddenly be covering up a lot of written tracks of data with your big, wide read head. So you cannot do random writes anymore with this. But in a cold storage facility, that's probably an acceptable trade-off, because you don't generally go and write to data in the middle of your cold stored data. You're generally writing blobs all at once. You know, your legal documents, you're doing backups of video security footage or something. And that's an acceptable trade-off. And I just think that's really cool that there's this way that you can write to hard drives that's only used in this very specific circumstances. So that's what Scaleway does, as far as I know, unless they've changed it. And they would not let me go to the data bunker while I worked there. So I don't have any photos of my own. Right. Flash memory. Last but not least. You have some of this in your pocket, probably. It's in smartphones, it's in tablets. If you've got a YubiKey or any other kind of like hardware token, that's using flash memory. And these work by using a circuit component called a MOSFET, a floating gate MOSFET. It's really complicated, but essentially what it does is it can hold charge, or it can not hold charge, 1 and 0. It stores electrical charge. And the thing about these devices that made them so handy for when I was a teenager and writing homework and taking it to school is that they draw power directly from wherever they're plugged into. They do not need their own power supply, unlike hard drives. Some hard drives draw power from the machine they're plugged into, external ones, but like your big one with 20 terabytes of pirated movies, that needs its own power source. These don't. This is great because they just sort of plug and go. However, flash drives, and this is SSDs, are flash drives as well, they have a few limitations. For a given block of storage, you can really only write to it all at once, not in patches. They also have a lifetime limit on how often they can be written to, because those MOSFETs, if you fill them up and then drain them and fill them up and drain them, they start to leak, they start to wear out. To mitigate this, flash drives have something in them that is called a memory controller, which essentially tries to spread the wear across all of the sort of different bits of the flash drive so that all of the components give out at once rather than one giving out way before everything else and rendering the whole flash drive unusable. Finally, those MOSFETs also do leak charge over time regardless of how far through their lifetime they are. So unlike magnetic tapes or floppy disks, if you put data onto one of these and then leave it in a cupboard for 10 years because you are NASA after the Viking lander mission, you might not get usable data out at the other end. However, if you have data on a flash drive that you want to make sure you don't lose, just copy it onto a new one and it starts the clock all over again. So it's fine. Yep. Right. We have learned all about the history and current state of data storage. We know a bit more about how and why we use various types for various purposes. You know, we use magnetic tapes for cold storage, and we use hard drives for every day, and we use the weird hard drives with the shingled magnetic recording if you're a weird data center. All the current methods of storage that I've just talked about are they're going to be iterated on over time. They're going to get progressively better and better. We'll improve the lifetime wear of flash drives, and hard drives will keep getting bigger and bigger, and we'll find ways to make the universe okay with the fact that we're making the really tiny magnets. But none of that is like particularly cool or futuristic or sexy. So let's talk about some stuff that is. DNA. DNA is very, very data dense. Microscopically small cells can hold the entire genetic code for an entire species. a team at Los Alamos National Laboratory has created an encoding, the Adaptive DNA Storage Codex, for turning computer-friendly binary into DNA-friendly pairs of A, C, T, and G bases. There are other encodings out there that are optimized for different things like density of data storage or error correction and things like that. The idea here is that you can create synthetic DNA that represents your data, and then that DNA can be stored very, very durably at low temperatures for decades. And we can actually do this today. There's nothing stopping us doing this today. People are doing it today. It's just not very efficient in terms of time. But in terms of data durability, as long as we know what those encodings are, that means that that data could still persist for a very, very long time. There is DNA data on the moon, courtesy of the Bereshit lander in April 2019. It did crash, so we don't know what state that DNA data is in, but it had synthetic DNA data on it. But if it isn't lost, the Arch Mission Foundation, who planned and executed that mission, they estimate it could still be legible if somebody knew how to read it in billions of years. Like billions of years. That's incredible. That's really, really cool. When I was first researching this, I thought it was talking about like putting DNA into like plant DNA, and then it's like, oh, I can propagate this by growing the plant that has the sort of inserted DNA in it. And apparently that's not a thing, and there's all kinds of ethical concerns with doing that, and that we might bring about the end of the world by creating a race of super plants that, I don't know. But that's not what this is. This is still very cool, though. And there were lots of different encodings being considered, and one of the things that people are trying to consider when they're building these encodings is how easy would it be for somebody to reverse engineer this? Because again, if we lose that encoding, you lose all the data that's stored, and people do want to mitigate that. Another type of data storage that is being looked at with an eye to data durability is Superman storage, also known as 5D optical data storage. That's a bit of a marketing name. I'll talk about that in a bit. The idea here is that you take a transparent, non-photosensitive material, so something like a bit of hardened glass or fused quartz, and you use a laser to engrave data within the 3D sort of material that you've got here. It's called 5D because it's a marketing thing. But what they're sort of getting at is like you have your three physical dimensions, like, you know, back and forth, up and down, left to right. And then you have what the angle is another degree of freedom, and how close you are to the thing as another degree of freedom. And they say, that's 5 dimensions. It's not, but it's a good name. So, so what happens is that depending on how close you are, what angle you're looking at, and where in the crystal or material you're looking, you can read data in different ways. The photo here is the Universal Declaration of Human Rights engraved into a piece of glass, and you can see they have done it in a way that it looks like the UN symbol, which is very cool and cute. Hitachi and Microsoft are both working on this concept, and the current bleeding edge stuff is being done at Southampton here in the UK. All of those teams are working on this with an eye to data durability, like the explicit goal of data durability. The data isn't going anywhere unless you drop the glass, which you absolutely can do. But as long as the glass is not like shattered, this isn't charge that's dissipating from MOSFETs. This isn't going to get erased by putting a magnet too close to it. You know, this is very, very durable, physically speaking. The encoding that's being used to turn data into engraving isn't yet settled, as far as I can tell, and that's the much more philosophically interesting and difficult problem. It may be, I don't know what it is, but maybe the Human Rights Declaration is all there in just like 7-bit ASCII or something. As long as we know what that is in like 1,000 years, we'd be able to get the UN Declaration of Human Rights back out of this piece of glass, which is really, really cool. And it's very dense as well, you know, it's quite small. That's really, really cool. So, the last thing that I have to talk about today, and the weirdest, and the one where I want to caveat very strongly that I'm not actually predicting this is going to go anywhere, but it's really cool, is time crystals. Do we have any condensed matter physicists in the room? Good. I have given this talk before and people have put their hands up and I was like, I am so sorry for what I'm about to do to your beautiful profession. So, this up here isn't a time crystal. There are no good photos of them, unfortunately. It is a space crystal. And like flash memory, you have some of this in your pocket because this is silicon, and silicon is a space crystal. The thing that makes it a space crystal is it has a repeating structure in space. You look at it, and then you move over a certain bit, and you look at it again, and they look the same. A repeating structure in space is a space crystal. Time crystals are the same, but they have a repeating structure in time. This is the best image I could kind of think of to try and display the concept that I'm talking about. A time crystal is an object whose lowest energy state, its sort of resting state, is one of motion. This doesn't break the conservation of energy because something quantum physics. They were first theorized to exist in 2012 by a theoretical physicist called Frank Wilczek, and in 2021, so only 9 years later, a team of scientists in the University of Hamburg made one in a lab. It didn't look like what you might expect. It was called, it's a Bose-Einstein condensate. And that is a state of matter, like, you've got liquid, gas, solid, plasma, and then there's like 13 others or something, and one of those is a Bose-Einstein condensate. It's what you get when you supercool boson gases. I personally hate when I open my freezer and I've accidentally made Bose-Einstein condensate again. And the reason that they're in this talk is because some very clever people think that we might be able to use them as storage for quantum computers. And that's currently an open problem, as I understand it, because in quantum theory, there's something called the cloning theorem. And what the cloning theorem says is you cannot duplicate quantum state. You can't copy it. You can only read it, and by reading it, you destroy it. Like with core memory, destructive readout. So any operation that reads from a quantum memory store is intrinsically destructive. And that means, that has certain implications for what we can use in order to store quantum data. But maybe it's time crystals. And I read the wiki. If you want to go and read up on time crystals, it's an absolute trip. I think I briefly understood them for about 3 seconds, had an out-of-body experience, and then went back to just being like, okay, I don't know what is going on here. But they're really, really cool. And the fact that we sort of went, well, the laws of physics say that this should be possible, I guess. And then it was only from 9 years from that moment that people made one is incredible. People are incredible. Scientists are incredible. So, on that note, conclusions. We have learned about storing data all the way from customer complaints in the Bronze Age through to encoding our data on DNA and putting it on the moon. This has been an incomplete and whistle-stop tour. And most of what I wanted to impart with this is that humans are really cool and creative, and we're very good at solving problems in increasingly complicated ways. If there's another takeaway from it, though, it is that data is useless if you can't read it. Data durability matters. When you encode data, you need to make sure that somebody is able to read it. Otherwise, there's no point in storing it. When we store data, it has to be with that concept in mind. And this isn't something that in our day-to-day job as software engineers we get to deal with directly, but it does come into play slightly when we talk about things like encoding real-world concept into code objects. How are we serializing that? Is it in a way that makes sense to the person who's going to have to deal with it at the other end? And we get into all ideas of domain-driven design when we start talking about those things. But it all interconnects, and the way that we store data is absolutely part of that too. All of the data is useless, and another person in the future, which might be you, knows how to get at it. But mostly, people are really cool, science is really cool, time crystals. Thank you so much for your time today. If you follow that QR code, it's not a Rickroll, unlike the first one. That will take you to a little feedback form where you can leave feedback for me if you're so inclined. And if you would like to give me feedback, I really value it. But more crucially, I have stickers. And if anyone would like stickers, please come up to the front. And we have 5 minutes for questions. No, sticker time. Oh, question.
Is that with the wires?
Yeah.
Is that where the term hardwired comes from?
Oh, good question. So the question was the core rope memory. Is that where the term hardwire comes from? Hardwired in? I don't know. I could see it being from a lot of different places. It would be cool, though, and it would make sense. Yeah. I can add another linguistics etymology fact to my talk. Yes?
So while the disk spin the same speed, does that happen with CDs and other?
Yes, I think CDs are generally constant angular velocity as well. The question was spinning disks and constant speed.
Do they also have different densities of data.
I believe so.
Yeah,
Yeah, they do. They do. Thank you. Cool.
Actually, about the spinning disk thing,
Mm-hmm.
you were talking about how Apple had this idea to do variable angular velocities, and it just occurred to me that that would be a great way to include, exclusive content only available to Apple.
Oh, yeah. Vendor
Which-
lock-in.
Which is, it gives its own implications.
Listen, if anyone's going to do it, I think it would be Apple, right? Yeah. Yeah, no, exclusive, Apple-only content that you can only get by using their specific floppy disk encoding.
And-
If they're going to bring back the floppy disk, I wouldn't be opposed, right?
And that has its own implications for encodability. What was the term you used? Like
Data durability, or yeah.
Data durability. Because if you run around doing, and we've already had problems with DRM, and
Yeah.
people can't get their own stuff.
So I name dropped the digital dark age. That's a whole thing you can go and research, and it's like a topic in its own right. But the concept there is that as we sort of encode things in like increasingly obscure ways, and do things like DRM and things like Netflix taking down movies before they've even really been released, and just like those are never ever going to be seen again, or whatever. Like, how do we do digital preservation in a way that is actually going to be resistant to the kind of things that go wrong over time when we lose information and we lose access to hardware? The digital dark age. It's a like scary idea, but lots of very clever people are working on really interesting ways to try and fix it, circumvent it, protect us against it. Yeah. Have 2 more minutes for questions, or we can just go. Question.
Is there a medium you didn't have time to talk about that you want to mention?
Is there a medium I didn't have time to mention? So the one that I went back and forth on whether I wanted to put it in the talk is a South American, and I can't remember which South American country it is, Kipu. And they what a Kipu is a series of, it's a fiber-based writing system. And it's strings, or like ropes, that are knotted in order to encode data. And there are a couple different kinds that people think that they may have been used for like maths and sort of going, okay, this is how much grain you owe me in order for this. But they've also been used for narrative recording. And one of the things that's really, really cool about them is that sometimes you need to see what the fiber is in order to know data, like information about what it's telling you. You need to be able to see whether or not it's knotted, so there's a topological aspect to it. But sometimes also you need to be able to touch the fiber, because your alpaca fiber and your something else fiber, I don't know, I'm blanking on South American animals that give you fiber. Your alpaca fiber and your vicuña fiber, right, for example, might look visually identical, but they mean different things, and you will only know if you touch it. That's really cool. And they were used as a sort of, not back channel isn't quite the right word, but they were used to encode secret communications during a civil war, I think in Lima. But don't quote me on that because I haven't got it in my speaker notes. But that's really cool. Kipu, Khipu is the search term that you want to look up, and they're really, really cool.
QU.
Oh, I think it's either, right? Yeah. Yeah, that would be the thing that I would want to put in. But then I was like, is it data if you're recording like a narrative? What constitutes data? And then I ended up writing a whole separate talk about
I would
that.
say that yes, because they use it to transfer the information regarding in the whole empire. Because it's really vast. So it was just to say like, oh, you know what? This province over there, they are like this amount of person, this amount of land.
Okay, so it was very definitely like quantifiable stuff.
We don't know for sure how to read it because it was lost in history. But for example, the things that we know is that, for example, red color means an animal.
Yeah.
So, and it depends if you just do 1 knot or 2 knots or whatever the heck. Like, there are books just documenting all the types of knots that they just made.
Yeah, like I started going down the rabbit hole of researching this, and then I went down a separate rabbit hole of like what counts as data, what am I going to include? Like there's a reason I didn't put cave paintings in here, because what they encode is not, you get into what is language, and it's like specific utterances, and you start having to learn about linguistics and semiotics, and that's a separate talk, which I also have, but I'm not doing here at this conference.
It was Incan, by the way.
Incan, okay, yeah. Like really, like so much fascinating stuff. I love all of this, all of the history of like stuff and people and technology.
It's pretty cool.
Yeah. All right, let me get you stickers.